All right, let's start with drawing weak acid, strong base titration, particulate model diagrams. So what we should really focus on here, a couple of things before we get started, because they kindly drew the beginning part for us for A so we know what we're starting with. So I'm going to outline a couple of things before we go into the full out drawing of this stuff. Now, we are titrating 0.1 of acetic acid with 0.1 of sodium hydroxide. Here's the volume added. And what it's showing you here for A, because at A, you're only starting with acid, nothing else has been added at this point, that this 0.1 of molar of the acid, and I'm going to use, HA to represent acetic acid, because writing out that formula, takes a while, and A minus to represent acetate. So for HA over here is being represented in this box by 6 particles. So that 0.1 is being represented by those 6 particles in there. And the only thing in there, of course, is the acid. So that anything that's in there at a large concentration is really just the acid. You have a very small, minute amount of the conjugate, a very small, minute amount of the hydronium. Not even worthy of drawing it into the model. Okay, because it's below 5%, right? So, things to consider when you're looking at these particulate model diagrams in a titration curve. Titration curve is a neutralization reaction. And you want to know your net ionic for the neutralization. So we have our HA plus our hydroxide. That's going to give us the water and the conjugate. In terms of this, it's acetic acid and acetate. Now the H plus the OH, that's going to give us the water, right? Sorry, didn't mean to do that whole thing. I meant to just say the H here, that H. Now what's left over once that H is pulled off is your acetate, and that's going to form over here. So you have the H being pulled off of the acetic acid, being neutralized into water with the hydroxide, and then we have conjugate floating around. That's one of the things we need to consider about the particulate model diagrams. The other thing we need to consider is that when you're adding in the sodium hydroxide gets added in where it breaks up into sodium and hydroxide. Now, these sodiums will be in a high concentration in the solution because they will be 1-to-1 with the hydroxides. Even though it's a spectator and it's just going to be floating around in there, you still are going to draw that in. It's part of the key. So that's what you would want to do, is draw that in. Now, we also have to consider this area different from the strong because this is the buffer region, where we're going to have both components in there. We're going to have both the acid and the conjugate. The acid-base pair will be in there together. That's going to be your buffer region. And sometimes it's easier if you start at the midpoint of the buffer region and look at it from that perspective at C here. And if you look at C here, the midpoint of the buffer region is halfway to the equivalence point. So this is 12.5 milliliters. The equivalence point is here at 25, as you can see, marked there by E. So halfway to the equivalence point means half of the base has been added. I'd like to start and look at C here, because we have to proportion our molecules based off of that. So we look over here at C. All right, we're at the midpoint. That means half of the acid has been neutralized into the conjugate base and the water. So if we're starting with 6 particles of our acid over here, how many should be remaining at C?
3.
We should have 3, right? So half of them are neutralized, right? I'm going to use blue to draw the acid. That's why I traced in that way. Use blue to draw the acid. So we're going to have 3 left over in here. like so. Sorry. Sometimes I'm artistically challenged. There we go, that's a little better. All right, there we go. 3 acids in there, but if we had 3 of these get neutralized, that means how much of this is produced? Also 3, good. So we should have 3 of the conjugates in there. I'm going to use red for the conjugate. So we should have 3 of our acetates in here floating around. But what does that also mean about the sodium? What do we got going on here for the sodium? How much sodium hydroxide was added if we neutralized 3 of the acids? How many hydroxides did that take? It took 3 hydroxides, so that means how many sodiums are in there? Also 3, good. So you kind of have to count the numbers as you're going, so you have 3 sodiums floating around in here. Like so. Very good. So that's the midpoint of the buffer region, the half equivalence point. This is also going to be indicated by the fact that the concentration of your acid is equal to the concentration of your conjugate base. Now remember, we just added 12.5 milliliters of the base, so all of those hydroxides combined with an H to form water, so they all left and went to form water. We didn't add enough to where there's going to be hydroxide left over. So I guess there'd be, no, not really. We're still, yes, definitely no, we would not draw in hydroxide at this point. Because it's all gone, it's all, this H here, this H has combined with the OHs to form the water. And there's still more of this in solution than there was of the hydroxide that we added. We know that there's 3 because if you look at how much volume was added, we know there's 3 acids because if you look at the midpoint of the buffer region, 12.5 milliliters of your base was added because it's halfway to the equivalence point, and the equivalence point was 25. So if we start with 6 to begin with, and we neutralize half of our acid, that means 3 are left over in there. Does that make sense? All right. Sure, no problem. Now something to consider here too. I don't know, well, we'll talk about this later as well, but the Hendy-Haas equation, pH equals the pKa plus the log of the base over the acid, like so. Okay, what you notice here at the midpoint of the buffer region, this one, C, is this is 3 to 3 right here, right? So that really makes this be the log of 1, right? And what is the log of 1? The log of 1 equals 0. So basically this part cancels out. So we have the pH equals the pKa. And that's kind of where that idea, where you're at the midpoint of the buffer region, I see here, that the pH equals the pKa, like so. So that's all good. Now, you can define like the particles in the middle, the beginning and the middle. Now we can look at B and kind of figure that out. Because B is before the midpoint of the buffer region. So in here, in that particular aspect, which one are we going to have more of, the acid or the conjugate? Going to have more acid, so it's going to be greater than, slightly greater than the base. So we need to draw somewhere between 6 and 3, of course, to where there's more acid than there is conjugate base. So I'm going to stick with like 4. We'll just go 1 up. 1, 2, 3, and 4 acids. 4 acids, right? Since we have a little bit more acid in here than we do base at part B, up there, we neutralize 2 of the acids, because we're not to the halfway point yet. How many conjugates should be in there? Yes, we should have 2 conjugates in here. Good. Now, how many sodiums should be in there?
Wait, why do we have conjugates?
2. Very good. 2 of our sodiums in there. Now, why do we have 2? Because we're saying that we start with 6, but we have a little bit more acid than we do base, so we neutralize 2 of the acids. If we neutralize 2 of the acid, that means 2 of the conjugates will be left over.
Oh, okay.
Okay, and that means we use 2 hydroxides to do the neutralizing. So that means that's why there's 2 sodiums present. Okay? So that's that's how this looks. Okay? The B is going to be a little bit more acid. Now I'm sure you can predict now for D, which one's going to be in higher concentration. So let's look at D.
The base.
All right, so D here, we are past the midpoint of the buffer region. So if we're considering that, yes, and we have our acid concentration. Can't write today, apparently. Our acid and our base. That means this is going to be greater. The base is going to be greater. Exactly right. And if we had 3 of our acid and 3 of our base at the midpoint at C, now we're going to go up to having 4 of our conjugate. I suppose you could do 5 too, but I'm going to stick with 4. And we're going to have 2 of the acids floating around. Remember, I'm using the blue here for the acetic acid and the red for the conjugate base. Now, how much sodium needs to be added at this point? Yes, 4 needs to be added. Because we added 4 hydroxides to neutralize 4 of the acids. That's why we have 4 of the conjugates produced. So 4 sodiums tagged along with the hydroxide and is now in there. So far, so good. Now the hard part. Get to the equivalence point, which is E. We know it's the equivalence point because it makes this nice inflection up here, right? That's our equivalence point. What do we know is true at the equivalence point? What happens at the equivalence point? What is the definition of our equivalence point? Not exactly, kind of close. The pH is actually above 7. It's not at 7, it's above 7 here. But what 2 chemical species are equal at the equivalence point?
Acid and base.
The acid, the HA, remember this was what we had. We had HA plus hydroxide giving us the water and the conjugate. At the equivalence point, HA, the H and the hydroxide here combine to form water. All of it's gone. So your H plus moles equal the OH moles. But that also means if all of the acid was neutralized, you have all conjugate base floating around now. So if we started out with 6 acids, how many conjugates should be floating around at the equivalence point?
6.
We should have 6 of our conjugates in here. Like so, right? Good. There's one other species in solution at the equivalence point. What is it? Yes, the sodium. So if 6 of the acids were neutralized by 6 of the hydroxides, how many sodiums should there be in there?
6.
6, very good. So draw in your 6 sodiums. Hopefully that's 6, okay. So that's easy enough. You have to realize that the amount of conjugate is equal to the amount of moles of acid that were added to originally to begin with. So in here at this point we just have the sodium and we just have the conjugate. These guys are floating around in here together. Now if we go past the equivalence point and keep adding the hydroxide, we're getting here 35 milliliters, we're now at F. We've added in extra hydroxide. So F, we're adding an extra hydroxide. So we should keep what we have at the equivalence point and transfer that because that's all still present, right? Then we figure out what we need to add. So we still have our 6 conjugates in here. We still have our 6 sodiums in here from the equivalence point. That did not change. Like so. But we've added some extra, but we only added 10 milliliters extra, not 12.5. If we added 12.5, I'd just add 3 of everything, right? So it's a little bit less than the 12.5 that we originally added here to get to the halfway point. So I'm just going to add in 2 more of my sodiums and 2 more of my hydroxides. So 2 and 2. So 2 more sodiums. 1, 2, but gonna use green for the hydroxide. So I'm gonna have some hydroxide and another hydroxide in there. So that's the basic gist of drawing the models as you go along, the titration curve. But they usually give you the amount they want you to start with. You've seen they give you those telling you how much to start with, so you have to show the progression. Or they could give you like the amount that you're at the midpoint, and then you have to figure out the original amount kind of thing by counting the particles. So what I want you to do with the other ones, the other 2, is of course try those on your own to be submitted for the assignment next week. Now we're going to switch gears and go back to working the titration problem. And hopefully maybe it'll make a little bit more sense now that we've kind of looked at the species along. So you want to have this one out, one with the chart. We're going to keep going here. We're going to work the first one together, and then you'll do the other 2 and you'll do the graphing of the 3 titration curves on the back. So you're just going to graph the pHs on the back and draw in the curves for each one. But we're going to start with the first one here and doing the weak acid strong base calculation. I'm going to show you a little trick too to make it go faster, somewhat faster. All right, so remember at the titration curve, when you haven't added any base yet, 0 milliliters of base have been added. We're starting out with only the acid in solution. Yes, this is the titration curve one, has like a chart on it. You could do it on a separate sheet of paper though. It's very much easily, you could just write it out as we go. All right. Consider the titration of 100 milliliters of acetic acid. Once again, I'm going to use the HA to represent acetic acid because this is, you know, a lot to write out every time, like so. So I'm going to use HA. And it's going to be titrated by 0.1 potassium hydroxide. They gave us the Ka, so we have the Ka value here in the problem. Calculate the pH of the resulting solution after the following volumes have been added. We're starting with the 0. The Ka for what? What are we writing the Ka for? It should be in the problem. Well, no, here I'll show you what you should write out for this one to show your work. I will show you what I would think the readers would want to see. And what I've seen in scoring guidelines before. Since this is just weak acid, because the only thing in there is the acetic acid, we have our HA plus our water, and that's going to make some hydronium and some conjugate. Now, of course, I'm referring, once again, because this is acetate and it's hard to write out, it'll take time to write it out every time. I'm going to use A-. And you can make yourself a little key like that if you have a really long acid and do that in the AP exam. I'm sure they'll accept that. Here is our reaction, though. And at equilibrium, we have 0.2 of our acid. We're going to subtract X. Remember, the water doesn't really matter. That's a liquid, doesn't change. This is going to be X, this is going to be X, right? Write out your expression. You want to do that to show your work. Ka equals the first product times the concentration of the second product, which is A-, over your reactant that you can put in the expression because water, once again, is just a liquid. Now we can just plug in our values. So we have 1.8 times 10 to the minus 5 equals x squared over the 0.200 minus x. Now what do we get to do with x here? We can eliminate x. All right. So eliminate x, 5% rule, all that good stuff. Then we just calculate and we can get x. Now which x do we care about? We care about this x. This is the one that's going to drive the pH, the hydronium. That's the one we care about for looking at pH. So 1.8 times 10 to the minus 5 times 0.2 and then square root that. Our concentration or x value, the concentration of our hydronium happens to be 1.9 times 10 to the minus 3. Yes, exactly right. Due Tuesday night. The rest of it will be due. So make sure you're doing it so you have your example to follow. Now that's the concentration of hydronium. So how do we find the pH from the concentration of hydronium?
Negative log.
Negative log. So we just need to do our negative log of our hydronium pH. Plug that in. And what do you get for your pH?
2.72.
2.72 is correct. This is our pH. So that's our starting pH, and that'll be your first point on your graph as you're graphing it. Very much so correct there. Easy problem, nothing's been added, just weak acid equilibrium. Now, if we were doing the opposite, we were doing the weak base being titrated by the strong acid, This problem would just be a weak base equilibrium problem. Be the same thing except for you'd have a Kb, and you would be looking for the OH, and then you would do 14 minus the negative log of hydroxide. So this problem, going the opposite way where you have a weak base being titrated by a strong acid, is just a weak base equilibrium problem. Now for the buffer region, because we're now going into the buffer region. This is the fun part. Consider the titration of 100 milliliters of 0.2 acetic acid by 0.1 where we've added 50 milliliters of KOH. Now if you look at these numbers, you can tell you haven't gotten to the equivalence point because 100 of 0.2 is not going to be neutralized by 50 of 0.1. Like that's not enough to neutralize, so we definitely aren't to the equivalence point yet. We are in the buffer region. Now this is the fun trick we get to do here. You all know, I'm sure you have this one ingrained in your head, but molarity equals the moles over the liters, right? Now if we use the molarity equation, it ends up giving us these really small numbers of moles. And you have to write 0.00 whatever, right? And it gets kind of annoying. So instead of using this, we're going to calculate it in millimoles. That way we're going to be dealing with whole numbers, and it's much easier to work with. So this is what the millimoles look like. You do molarity equals millimoles over milliliters. Because they are both factors, that are 1,000th of the original. So that's going to equal. And if we do millimoles over milliliters, now we don't have to convert milliliters. It's easy. But to start this problem, we have to figure out the millimoles of both our acid. Remember, we're keeping this as HA, and our base. So I'm going to start with the acid. Let's go ahead and calculate that. So here for HA, we have nope, that's not all right. For the acid, we have 0.200 equals the millimoles over 100 milliliters. All you have to do is multiply your 0.2 times 100. So how many millimoles is that going to be? That one you can do in your head. You don't even need a calculator. What's 0.2 times 100? 20. Good. This is 20 millimoles.
I have to write
20 millimoles. Very good. Now let's calculate the millimoles for our hydroxide. Right? Because we need to figure out what's left in solution here. So for our hydroxide, we have 0.1 equals the millimoles over the, in this case, 50 milliliters, right? So how many millimoles of hydroxide did we put in there? 5. I know, right? That's a nice, easy number. 5 millimoles of our hydroxide. Now, because we're in the buffer region, I know I have to keep track of how much of each thing is in there. And then I have to do something called the BCA chart. Because I need to figure out what's still left floating around in solution. Does everybody remember the BCA chart from the notes? So what reaction we have going on here? We have our HA plus our hydroxide. That's going to give us our conjugate, our acetate, and water. So before, change, after. We don't really care about the water. Once again, that doesn't matter. But we're starting out with 20 millimoles of our acid, 5 millimoles of our base, and 0 of our conjugate. Which one's going to run out, the acid or the base? We have 20 of our acid and 5 of our base. Which one's going to run out when they react? Yes, the base is going to run out. Very good. So this is going to subtract 5. This is going to subtract 5. This is going to add 5. Because every time you neutralize one of the acids, you make a conjugate. This goes down to 0. This is now 15. And this one is still 5 over here. But this is what it tells you. And this is important. You have both of the buffer components in there. You have the weak acid and its conjugate in there. That means this is a buffer. You have both components in there. You should recognize it as a buffer. And then you should use the Hendy-Haas equation because it's the easiest way to go. Henderson-Hasselbalch equation, pH equals the pKa plus the log of the base over the acid. Now this is important because it makes it so much easier to plug in the numbers and get the pH, and it's faster than trying to do it as an equilibrium problem. So what we're looking at here, also remember from the notes too that yes, it says concentration, but remember that's just a ratio of the acid to the base. So it doesn't matter if we're using the mole ratio or the concentration ratio. I'm not going to recalculate these concentrations here because they would both divide by 150 milliliters because you have 50 here and 100 here. All we would do is divide them both by 150. So the ratio number stays the same, right? So why bother doing that? That's a waste of time. We just plug in everything now, so the pH equals the negative log of 1.8 times 10 to the minus 5 plus the log of, here I'm going to have to write that down here, sorry, I ran out of room. pH equals the negative log of 1.8 times 10 to the minus 5 plus the log of, we want the base 5 divided by the acid 15, and we will calculate our pH. So what do we get for the pH at this point in the buffer region, where we have more acid than we do base?
4.27.
4.27 sounds correct. So pH equals 4.27. Now, we know we have more acid than we do base, so this is before the halfway point. If it was at the halfway point, they would be equal, right? But we're before the halfway point, so our pH is not going, it's going to be a little bit lower than the pKa. And so that is correct. Very good. Now once again, looking at the next question here, we have titration still going on. Now we're going to add 100 of our KOH. And yes, I know it tells you on the paper that this is the halfway point, but most of the time they're not going to tell you you're at your halfway point. You have to figure it out first. So let's figure it out, show you how to represent it, write out the work. And all of these that are in the buffer region is sort of like a partial neutralization, because you only neutralize half of or part of it. And in a partial neutralization, you're always creating a buffer when you have a weak acid and a conjugate base. So this is always going to create a buffer if you're only partially neutralizing in that particular case. So here we know we have 20 millimoles of the acid. We already know that because that value is not changing. We figured that out last problem, right? We have 0.2 and we have 100 of acid in there, and that's not going to change. However, what is changing is now the 0.1, we've added 100, right? 100. So for the OH this time, we have 0.1 equals the millimoles over 100 milliliters. So how many millimoles do we have of our hydroxide? 0.1 times 100 is 10. So you have 10 millimoles of our hydroxide. Same idea here to note it's before the equivalence point, so we're in the buffer region. Set up the BCA chart. We have our acid plus our hydroxide. That's going to create the conjugate in water. And we don't really need to care about the water, but we had 20 millimoles here. We had 10 millimoles being added here, no conjugate. Now we would subtract the 10 from both sides and add it over here to the conjugate side. 10 from both the reactants here. And then 10 here. So what you should notice, we have 10 and 10. 10 of the acid in the pair, 10 of the conjugate base in the pair. So they're going to be equal in this case. That means when we do the pH equals the negative log of 1.8 times 10 to the minus 5 plus the log, it's now going to be 10 over 10. And what do we know about this? This part is going to equal the log of 1. So, sorry, I guess I should put the log of 1, which equals 0, like so. Then that means this completely cancels out of the equation. And now all we have to do is the pKa equals the pH. So what is the negative log of 1.8 times 10 to the minus 5?
4.74.
So yeah, this right here, 4.74. And if you remember from the previous problem where we had slightly more acid, it was 4.27. So a little bit lower, but not that much lower. Because the buffers do like to resist their, yes, they do like to resist that changing of the pH, right? They keep it in a range. So 4.74, there you go. So first problem was weak acid. The next two in the buffer region, you do the BCA table, BCA chart, and use the Hendy-Haas equation. Makes it easier. This next one, though, this is the hardest of the titration curve problems. It's the equivalence point one. And yeah, I know it tells you it's the equivalence point, but if you looked up here at the values and what was added, you should be able to be like, yeah, we're at the equivalence point. Because we have 100 of 0.2, and now we have 0.1, 200 being added of the 0.1. So that's going to end up being equal. So if you look at those numbers and you go, oh, we're going to be at the equivalence point, then you can continue on moving through here. If you can't figure out by looking at that you're at the equivalence point, you set up a BCA chart, do the millimoles. But if you do the millimoles, we already know that this one is 20 millimoles for the acid. What is 0.1 times 200? 0.1 times 200 is 20 as well, right? So we have 20 millimoles of the acid, which is going to be 20 millimoles of the hydroxide, because, you know, 0.1 equals the 200 here. That's where we get that number from. So 20 equals 20. At the equivalence point, we know the moles equal the moles. So at the equivalence point, though, that means all the hydroxide and the original acid have been neutralized out. The only thing left in there, right, this point, because we had our HA plus our hydroxide, gives us the conjugate and the water. These two things are gone, but what do we have floating around in there? we have the conjugate now floating around in there. And we know the conjugate base of a weak acid is a basic anion. So it's going to react with water. It's going to react with water and form a little hydroxide. So our new reaction here is going to be the conjugate plus water is going to give us the acid and some hydroxide. This is why the pH at the equivalence point is always higher than 7 for weak acid being titrated by a strong base. Well, we have to figure out the concentration here of our weak base because the conjugate base is now acting as a weak base. So let's think about this. We need to know the mole amount over the liter amount or the millimole amount over the milliliter amount to figure out our concentration of our conjugate. Well, if we started with 20 of this, 20 of our acid, how much conjugate should be around? 20 of the conjugate should be around. And yes, we do need to do the new volume. So the molarity, we know we've got 20 millimoles of our conjugate because we had 20 moles of our original acid. But what is the new volume? Definitely need to look at that. We had 100 milliliters plus 200 milliliters, right? So new volume, 100 plus the 200, that gives us 300 milliliters. Yay! So that's what's going to go on the bottom here, 300 milliliters. This is going to give us our concentration of our acetate, our conjugate base. So what is the concentration of our acetate?
0.666.
Yeah, I'm going to go with 0.0667. 3 significant figures since the molarities are in 3 digits. Okay, so I'm just going to keep for now. Alrighty, so far so good. Now we know this value. So for the equilibrium, we can put this in. Minus x. This is going to be x. This is going to be x. We don't care about the water, remember. It doesn't do anything. So we have this. This is wonderful. We have our concentration of our weak base. We can set up our expression. Kb equals concentration of the first product times the hydroxide over the original base. However, which value are we missing that we still have to find? We're missing something.
The kb.
We need Kb. What did they give us in the problem?
K8.
They gave us Ka, so we need to find Kb. How do we find Kb when we have Ka? What can we use? Kw, exactly right, because Kw equals Ka times Kb, like so. Woohoo! So this is 1 times 10 to the minus 14. Kw is on your formula sheet. So Ka was 1.8 times 10 to the minus 5. So we can find Kb now. So calculating Kb, you should get 5.6 times 10 to the minus 10. If you plug that into your calculator, that's what you should get. Now we're ready because we have Kb. We have our concentration of our conjugate. We have the concentrations of our products for the weak base equilibrium. All we have to do is plug in and calculate. So 5.6 times 10 to the minus 10 equals x squared over 0.0667 minus x. Eliminate x. Doing that 5% rule, like so. Let's get rid of that. And then we end up with
3.74 times 10 to the negative 11. It's not right. Oh, I forgot the square root.
square root it for us, please. Yes, do that, please.
6.11 times 10 to the negative 6.
6.1 times 10 to the minus 6 molar sounds good. Remember, we're looking for this x, because this is the one that determines our pH, the hydroxide. So now we know our hydroxide concentration. What do we need to do at this point? Last step.
Put it into
The negative log equation, yes. This is hydroxide though, so we need to do 14 minus the negative log of the hydroxide. That's going to give us our pH, right? I should have written it differently. Hold on. 14 minus the negative log of hydroxide. Let's go ahead and do that. Put that in. 14 minus negative log of 6.1 times 10 to the minus 6. And what do we get for our pH? Yes, 8.79 looks good to me. 2 sig figs because the Ka and Kb's are only have 2, so we go with 2. So that means we have 2 decimal places added to our pH value. And yes, we got it correct. All right, woohoo! Now for the easiest part of them all is the excess problem. At the tail end, you're going to add in a little bit extra hydroxide. So we're going to have to recalculate our hydroxide concentration. And then we can figure out the pH at the top end of the S here on the titration curve. Now, go back to your original values. We already know that we had 20 millimoles of the acid, right? That's all that was ever added. That's the amount that got neutralized. However, at 250 milliliters at 0.1, how much of that base was added? So here, for our hydroxide, we had 0.1 equals the millimoles over 250. So how many millimoles of hydroxide were added entirely to the system here?
20-something.
So yeah, so this equals the 25 millimoles that were added. So we have 25 millimoles of our base and 20 millimoles of our acid. That means that we can figure out how much is left over. So 25 millimoles of the hydroxide minus the 20 of the acid. That's going to leave us with 5 millimoles of our OH left over. And just like before, we know the millimoles, but our volume has changed again because we added some more stuff in. So what is our new volume? What's the new volume? Yes, we have the 250 from the base plus the 100 from the acid. We have new volume, 350. So we put that on the bottom here. To get our molarity, we take our 5 millimoles and we divide it by 350 milliliters. So what is the concentration of our hydroxide then? Concentration of the hydroxide? 0.014. Exactly right. That's what I would go with. And then, last but not least, we have to find the pH. We have hydroxide. It's the 14 minus, yes, the negative log of our 0.014. And what do we get?
12.1.
12.15, sounds good to me. 12.15. Exactly right. Now just a few things with regards to the, we just did the weak acid being titrated by the strong base. We do the weak base being titrated by the strong acid, everything's pretty much just reversed. The first problem where you haven't added any acid is a weak base problem. The buffer region ones are pretty much the same, you use Hendy-Haas for those. You get to the equivalence point though, the equivalence point is going to be a weak acid equilibrium, and you have to find Ka, and you have to find the concentration of the weak acid before you begin. So it's just the opposite. And then here, if you get to the excess problem at the end, instead of finding the hydroxide, you're finding the amount of H+ that's been added in excess. So they're just opposite, but they are the same type of problems as you go along. Just remember at the equivalence point though, for the weak base, strong acid, you're going to be finding the concentration of the conjugate acid, and then you're going to have to find the Ka from the Kb. So it's just the opposite way there.